Well, thank you very much. Can you all hear me well? Is the microphone working properly then? Okay, excellent. Let's see if I can get this thing started. Excellent. So we're online. Okay. I'm delighted to be here. This is the first talk I've given at Griffith, and I've been in LA since '83. And I've been contributing to the Griffith Observer now and then since '77. So I have a long history of association with this place. And again, it's really nice to be here. How many of you have a meteorite collection of some sort, even a few meteorites? There's a number of people there. We were just in China a few months ago, and meteorite collecting is now a big boom in China. And so we were there to sort of get their collecting off the ground, giving public talks like this as well. So all over the world, you have a lot of good company. I'm a very informal guy, so if you want to just shout out questions, complaints, or innuendos while I'm talking, feel free. I wanted to start off with this to sort of give you, believe it or not, a simplified version of what kind of different meteorites there are. Just very briefly, we have primitive meteorites, the so-called chondrites. They're called chondrites because they have these sub-millimeter sized spherules formed from a melt called chondrules. I'll be talking about that in a moment. So these are from asteroids that never melted. The other ones, the differentiated meteorites, are from asteroids or planets that did melt. Like the Earth is a differentiated object. It's called differentiated because it has different layers. It has a metal core, a stony mantle, and a stony crust, so it's differentiated into different layers. So most of these things are from asteroids that melted. They're differentiated asteroids. These are hence called differentiated meteorites or igneous meteorites. They formed from a melt. And as I delineated them here, all these guys are from bodies that have been sort of totally melted. These things formed from a melt, and those here in this sort of putrid yellow color here are from groups of meteorites where at least some of the members have been heated appreciably. And I'll talk more about these different processes in a minute. Okay, so the chondrites derive their name from chondrules, which is Greek for grain or seed, these small little sub-millimeter sized objects, sort of as what we see here. They're round, surface tension has made them this shape, and let's just see how abundant they are. They're sort of like dewdrops on a leaf. They precipitate from a melt or they condense from a gas, and surface tension molds them into these spheres or spheroids over here. And if you look at a chondrite here, all these little round objects here are chondrules. You can see that these things are chock full of chondrules. And here's another ordinary chondrite here. I'll talk about that also in a moment. You can see that it's mostly supported by all these chondrules. These kinds of meteorites can contain about 75 volume% chondrules in them. So they're mostly just chondritic rocks, hence they got their name from their abundant constituents over here. Another important, though less volumetrically important constituent are these so-called CAIs, calcium aluminum inclusions, or refractory inclusions. They get their name, calcium aluminum obviously, from they're rich in the elements calcium aluminum and titanium. Also refractory are those elements that condense at high temperatures. If you have a gas of solar composition that begins to cool, the first elements that come out at the highest temperatures are the refractory elements, including calcium aluminum and titanium, rare earths, and so forth. These are the oldest solids that formed in the solar system. They are, let's go back. They're 4.568 billion years old. They've actually been able to measure them with that degree of precision. They're moderately abundant in carbonaceous chondrites. What are the major groups of chondrites? And they can comprise up to about 10 volume% of these rocks. They're rare in the other chondrite groups, but they do occur. They may have, the interesting thing about them is that you look at the different chondrite groups which formed in different areas of the solar system, all of them contain at least a few of these refractory inclusions, which means, and interestingly, they all have about the same oxygen isotopic composition, which means they all formed in the same oxygen reservoir, probably in the same place. And so the current thinking is that they may have formed close to the sun and then got propelled far across the solar system after their initial formation. Now let's look at some of these things. This is the famous meteorite Allende, which fell in Mexico in February 8th, 1969. All these white inclusions here, and here, are these CAIs, these calcium aluminum inclusions, the refractory inclusions. We can see that they're very abundant in these rocks. And yet, if we look at a X-ray map of these things, we call these red, green, blue maps, RGB maps, and you can see that they're really not that abundant compared to chondrules. The red stuff is the chondrules. It's rich in magnesium. The ones rich in calcium and aluminum are the blue and the green and the purple and those little shades. We can see that if we look at the rock as a whole, the calcium aluminum rich inclusions constitute just a relatively small percentage, a few percent of the rock compared to the chondrules. The chondrules really are the most abundant constituent here. Now, to show you how important the chondrites are, if you were to, we know that the sun is made mostly of hydrogen and helium. If we were to take the hydrogen and helium away from the sun, what would you have left? Not much, but it would still weigh more than 6,300 times as much as the Earth. And it would have the elements in the same proportions that we find them in the chondrites. In other words, the magnesium to iron ratios and the thulium to uranium ratios, they would all be the same in the chondrites as they are in the sun if we took away the hydrogen and helium. This is important because it means that the elements that we're able to condense from the gas and form solids are the same material in the sun as in the chondrites and in the Earth and in the moons of the solar system and in the asteroids and in the comets. They all form from the same material. Now, the sun is only different because it's so big, its gravity was able to quantitatively attract the hydrogen and helium from the big cloud of gas and dust we call the solar nebula. But minus that, we subtract that, we have the same stuff that's in the chondrites. We can see that thallium and thulium and praseodymium, lanthanum, beryllium, cerium, lead. I see I took chemistry. These things are in the same proportions as in the sun. Here is the ratio in these meteorites, these so-called Ci carbonaceous chondrites. Here's the ratio in the sun. If everything was exactly the same, it would be on this one line. We can see that all of them, most of them are. Hydrogen and helium would be on the 34th floor above the roof, but we're forgetting that. Boron and lithium are sort of used up in nuclear reactions. Lithium, maybe there's a lot of papers about the lithium abundance in the sun being sort of dredged up from depth or locked into lower levels of the sun. The lithium abundance is a controversy at present. The nitrogen, the carbon, and the oxygen are above the line because they're incompletely condensed. There's nitrogen, carbon monoxide, carbon dioxide, water vapor still in the gas, and so some of these elements remained in the gas, were not able to quantitatively condense into solids, and so they're more abundant in the sun than they are in the solid materials, the meteorites. But anyway, this shows you how important meteorites are because they're the building blocks of the solar system. All the bodies in the solar system formed from these materials. And the chondrites are the unmelted asteroids. They give us the clues for what the solar system was like, how the solar system formed 4.5 billion years ago. These meteorites are called primitive for that reason, or undifferentiated because they did not melt. So even though, however, the chondrites have not been melted, that doesn't mean that they're pristine, that nothing's ever happened to them. They weren't able to escape alteration completely. There are three basic kinds of alteration processes which have affected these things. One is thermal metamorphism, which I'll talk about in just a moment. It causes the fine-grained material to become coarser. Some of the volatile elements like water and the rare earth and the noble gases and carbon and some of the more volatile metal elements like indium have been boiled off, if you will. The other process is aqueous alteration, alteration by water. There was either ice or clay minerals bound with water in their crystal structure, which were heated and the water escaped and then seeped through the meteorite, causing alteration. That's another one of the processes that affected it. And as you can imagine, since they're on small bodies with no blanket of air, shock metamorphism, they get banged up a lot by other meteorites hitting them. And so when a rock is heated extensively, it's said to be metamorphosed. There's different kinds of metamorphosis, as you know. Gregor Samsa woke up one day to find it had been transformed into a giant insect. And in Ovid's metamorphosis, Narcissus, who was in love with his own reflection, was transformed into a flower. And when we were all in grammar school, we learned this in biology, that we've gone from a caterpillar through a chrysalis to a butterfly, and so that's metamorphism, which means change from one form to another. Thermal metamorphism is change caused by heat. And so just like Marco Rubio, I'm going to have a little bit of water. For historical reasons, the least metamorphosed meteorites are called type 3. I won't go into the details of it, they're rather boring. And the most metamorphosed meteorites are called type 6. And so the type 3 to type 6 progression is increasing degrees of metamorphism. So let's see what happens during this. In the type 3, the least metamorphosed chondrites, the minerals are unequilibrated. That means that one mineral of one particular mineral, let's say an olivine, which is a magnesium silicate, may be right next to another olivine grain, and they'll both have rather different iron to magnesium ratio. So the variations will be significant. I'll show you a picture of that in a moment. The chondrules themselves have glass in between the mineral crystals in them. And the textures are unrecrystallized. It actually has abundant pre-solar grains. These are grains formed in supernovae and Wolf-Rayet stars and asymptotic giant branch stars for the astronomers among you. And these things are, these small micron size to several micron size inclusions are older than the solar system. They're from the atmospheres of dying stars which got incorporated into these primitive meteorites. When you start metamorphosing the meteorite, they get destroyed. So if you want to learn about do astrophysics through meteorites, we have to look at the least metamorphosed ones. And then going from type 4 to type 5 to type 6, the minerals begin to equilibrate, the textures get more recrystallized, the chondrule glass disappears, devitrifies, and become coarser grains, the volatiles start disappearing. And so anyway, so the cloud of gas and dust from which the solar system formed is called the solar nebula, and the type 3 chondrites are our best, most pristine representatives from that. If you want to go back to try to understand how the solar system formed, these are the chondrites to look at. Okay, so let's look at the difference in texture over here. One of the least metamorphosed chondrites is my friend from India called Samarcona. It's a type 3, that's what this 3 here means. The LL is the particular kind of asteroid it's from. It stands for low total iron, low metallic iron. And we can look at the texture. These are both of the same scale. This box is 2 millimeters long. And we can see the textures here. We can see these chondrules and chondrule fragments are really sharply defined. And here's a type 6 chondrite, the most metamorphosed variety from the same asteroid. And we can see that we can hardly see the chondrules at all. If we use our imagination, we can trace out a few things there. But they've been totally recrystallized. Let's look at the compositions of the minerals in them. This is the olivine grain, the magnesium silicate. And I probed one grain, then the next grain, then the next grain, and the next grain, and I plotted them over here. And here, this is just a function of their composition. We can see that it's really unequilibrated. The olivine grains, the grain-to-grain compositional differences are significant. There's a lot of heterogeneity in its composition. Yet, when I probed this type 6 chondrite over here, they're almost all the same. Diffusion has caused the iron and magnesium elements to migrate around and try to reach equilibrium. And so all the minerals in the rock have essentially the same composition. That's due to thermal metamorphism over here. The second alteration process, alteration by water, is aqueous alteration, it's called. Heating on the asteroid has mobilized the water. Either there was ice that accreted with it, or more likely, we had clay minerals like montmorillonite or kaolinite, which has OH bound in its crystal structure. You heat that up, the OH can come out of the crystal structure, form water, which can seep through the meteorites and start altering it. They can change some of the minerals to clay themselves. It can start devitrifying the glass, and it causes oxidation of the metallic iron nickel. It turns into magnetite, and it turns into other iron oxides. It can turn into hematite, and so in other sulfides and carbides, all due to this aqueous alteration. The third major alteration feature is shock, sort of like this picture over here. Here is an olivine grain, which I took and a picture of, and all these little streaks here are little curvy linear trails of small blebs of metallic iron nickel. The metal melts at a lower temperature than the silicate, so the shock came in. The heating from the shock caused the metal to melt and then blast through fractures in the olivine grain, and then because of surface tension, it withdraws instead of a straight vein. It withdraws into little blebs, sort of like if it's raining lightly and you're in your car and you're brave enough not to put on your windshield wipers, you'll see sometimes the water will run down the surface of your car, and then if it just sits there, it'll bead up into different little beads instead of just forming and staying as a continuous little trail, as a continuous stream. It'll bead up. The same thing happens to the metal blebs over here. And you can see this one olivine grain has metal blebs all over the place. It has all these trails all over the place. It was really, really shocked over here. Another way to look at it is the shock can damage the crystal structure of the olivine. If you have an olivine that's totally unshocked and you put it in the polarizing microscope and you put in what we call these different cross polarizers over there, the grain will undergo extinction like this and it'll turn dark. Here it's nice, and then we rotate the microscope and it turns dark, and we can see it all turns dark at once. The crystal structure is intact, it is undamaged. And yet with shock, it can be damaged, and we look at this, it sort of looks like a stained glass window as it rotates. It is broken apart into different little domains, each a slightly different crystal. It's become polycrystalline, and each of these goes extinct differently. The rock has been, again, shock damaged, and we can see it very nicely in this picture here. A few other indicators of shock are these. The metal is normally isolated grains all over the place. I'll show you a picture of that in a moment. And yet if the metal gets melted and mobilized and injected through fractures, you can get these metal veins, like this guy over here. Other minerals like chromite, a chromium iron oxide, and plagioclase, which is a sodium, calcium, potassium silicate. When the two of them are together, they melt at a lower temperature than either component alone, and it forms these assemblages. Plagioclase is the dark gray stuff here, and chromite is the lighter gray here. And these different assemblages are called chromite plagioclase assemblages, and this is something I described about 15 years ago as another shock feature, another indicator that these rocks have been shocked. An unshocked chondrite will look like this. The dark stuff there is the silicate, and we can see that the metal grains, the white stuff here, is homogeneously distributed throughout the rock. And that's what an unshocked rock would look like. Everything's fine, it's undifferentiated, and yet when it gets shocked, things happen. Also, when it gets melted, the metal and the silicate separate. They form two immiscible liquids. They cannot dissolve in one another. Just like water and oil are immiscible liquids, the water is denser than the oil, so the water sinks to the bottom of the vessel. The oil is lighter, and so it rises to the top of the vessel. When you melt a metal silicate mixture like that guy, the metal and the silicate separate. They form two immiscible liquids, just like the oil and the water. The metal liquid is a lot denser than the silicate liquid, so the metal liquid sinks to the gravitational center of the body to form a metal core, just like the Earth's metal core. And the silicates rise to form a mantle and a crust. Meteorites that were melted in their parent asteroids are said to be differentiated. These meteorites are the achondrites. They're called that. They don't contain chondrules. They're igneous rocks formed from molten magma. Just as atheists are people who don't believe in God, achondrites are meteorites that don't believe in chondrules. Okay, as of today, I checked, there are about 350 meteorites from the moon and about 215 meteorites from Mars that have been reported and analyzed in the literature. Both of these bodies are large differentiated objects, and so we have meteorites from the moon and meteorites from Mars. Hundreds of them now, over 500 of these things, approaching 600 meteorites from the moon and Mars. When I started out, we didn't have any, but now we do. We know the lunar meteorites are from the moon because we've compared to the Apollo samples that the astronauts schlepped back from the moon. And there's also 3 Soviet Luna missions which brought back about 300 grams or so of lunar material. We can compare them to that too. Just as an aside, back during the Apollo era, the United States sent astronauts to the moon, and that was a tremendous effort. But the Soviets, back in the 1970, 71, sent robotic spacecraft, unmanned robotic spacecraft to the moon to retrieve samples and bring them back to Earth. I think that's a remarkable technological achievement. And we were able to get material from that. Now, we're confident that the meteorites are from Mars. We don't have any rocks returned from Mars. So how do we know that these are meteorites from Mars? And because we sent the Viking spacecraft to Mars, landing in 1976, and they measured the Martian atmosphere. And now there are 6 meteorites, which we now call Martian meteorites because we know they're from Mars. Why? Because they have trapped air bubbles and melt inclusions, which have exactly the same composition as you see here as the Martian atmosphere measured in situ on the surface of Mars by the Viking landers in 1976. So we have trapped Martian atmosphere in there showing that they're from Mars. And now that we know these meteorites are from Mars, we can look at their deuterium abundance, we can look at their oxygen isotopic compositions, and we can see, they also form a group and they're distinct from other meteorites in these ways as well. But this is how we anchor them to being Martian. Okay, all the other meteorites, the other 68,000 meteorites in our collection are thought to be from asteroids and from the asteroid belt right there, orbiting merrily between Mars and Jupiter. Differentiated meteorites come from differentiated asteroids, as well as, of course, the Moon and Mars. And the chondritic meteorites, which are undifferentiated, come from undifferentiated asteroids, asteroids that never melted. So let's look at the differentiated ones for now. These are basaltic meteorites. Basalt is a very common rock on the Earth. These are derived from the crust of a melted asteroid. They may have reached temperatures of about 1,200 degrees Celsius. Basalts are on very many different bodies in the solar system. Here's the Earth. Here is Devil's Postpile in California. How many of you have been to Devil's Postpile? Those of you who have your hands down, shame on you. You need to go to Devil's Postpile. It's a beautiful area up there, and this is a magnificent structure, and it's not far away. No, it's not like that. These are basalts which cooled and formed these little hexagonal cooling cracks on there, and they make these columns, and there's a basalt flow. It's really pretty, and there's a park there. You can picnic there while you're eating. It's very nice. The largest volcanic area on Earth is the Deccan traps in India. These are also flood basalts that are all over the place. I've never been there, but maybe someday I'll go. And a sop to our sponsor, United Airlines. We have basalts over here. The Maria on the Moon, the dark areas on the Moon, are flood basalts over there. And thanks to United, we can see them in this picture as well. Venus has these sort of pancake volcanoes. These are shield volcanoes, these round ones on Venus. Venus' surface temperature is so hot, lead would melt if it's put out there, and the volcanic basalts just sort of ooze out of the ground and just flow like molasses around, forming these sort of isotropic circular pancake dome volcanoes on Venus. Over there. Mars has basaltic volcanoes here. Here's the Tharsis Ridge on Mars. Here's Olympus Mons, probably the biggest volcano in the solar system. Why is it so big? No, it's not the gravity. Not directly, anyway.
No tectonic plate movements.
No tectonic plate movements, right. So if we take the Emperor's Seamount chain and the Hawaiian Islands, they're sitting over a hot spot in the Pacific Ocean, and the plates are moving over it, and so the islands don't get too big. Mars has hot spots as well, or at least did, and it just sits there stationary because there's no plate tectonics, and so the mountain gets bigger and bigger and bigger and bigger. This is about the size of Colorado. So it's pretty big. That's Olympus Mons over there. The differentiated meteorites come in several varieties here. I won't go through all the different kinds, but the most common ones are the stone or stony meteorites, like the basaltic ones. There's the stony irons, which are half metal, essentially, and half stony. And then there's the iron meteorites. These are mostly from the cores of the asteroids that melted. Just like the Earth has an iron core, asteroids that melted have iron cores as well. And we have iron meteorites from these cores. So how do we get them from the cores of these? How do we get them to our lab if they're from the cores of the asteroids?
Impacts.
Yeah, impacts. We have to shatter the asteroid to expose the core, knock fragments over them, and have them come to UCLA. So here is a typical example of an asteroid that melted. We'll have a solid iron-nickel core. We'll have an olivine-rich silicate mantle. We'll have a basaltic crust on there. And Vesta, which the Dawn spacecraft has been to recently, probably looks somewhat like that. Oh, here's a picture of it. my goodness. It's 525 kilometers across, visited by the Dawn spacecraft in 2011 to 2012. And if you go to YouTube, put out Vesta rotation, and you'll see a couple of really cool videos of Vesta rotating. It's really worthwhile. I don't have a movie for you, but you guys can go to YouTube and do it yourself. Vesta rotation in YouTube, and you'll be able to see it rotate. It's really cool. Here's another picture of Vesta. It's, you know, when I was growing up as an astronomy major, Vesta was this tiny little streak of light. When Ed Krupp was growing up, they probably didn't even discover it yet. But now it's a real world over here, which is just so cool. Pallasites are stony iron meteorites. These are from the core mantle boundary. The metal is from the core, the silicate is from the mantle, and these are metal silicate mixtures from the boundary, from the interface between the bottom of the mantle and the top of the core. We've captured that area of the differentiated melted asteroid in these stony iron meteorites, these pallasites over here. They're the most beautiful of meteorites. Most people think they're the most aesthetic looking over there. They're really pretty. Over there. And if we have a schematic diagram of an asteroid like Vesta, we will have a metal core here. One of the groups of irons is called 3AB, again for historical reasons, and irons like that will come from a melted asteroid sort of like Vesta. They didn't come from Vesta because Vesta is still intact, so we couldn't extract the core from it, but we've extracted the core from, or not me personally, but the core got extracted from another asteroid that was like Vesta, probably smaller though, and we have that material there. And we have the so-called HED meteorites, the Howardites, Eucrites, Diogenites. These are basaltic meteorites. Diogenites are more rich in the mineral olivine, probably in the mantle. Basalts, the Eucrites, are from the crust, and Howardites are a mechanical mixture of the two in the regolith, in the surface soil of an asteroid like this. So sometimes people in the meteorite literature will say HED a lot, and that stands for Howardites, Eucrites, and Diogenites. Eucrites are just basalts. Okay, the iron meteorites, most of them come from the cores of differentiated asteroids, and they have this pattern here, which is called what? Some of you know. The Wittmann-Steiten pattern, right? And it was discovered by a guy named Thomson, but Alois von Wittmann-Steiten published first. So that should be a clue to people. So if you discover something, dash it out there so your name is attached to it. If we look at the different iron meteorite groups, these are all from asteroids that have melted, and we can see that they have different compositions. Here I'm plotting iridium versus nickel, and we can see that there's all these different little sticks and balls and carrots and things like that, all these different little areas here, and they're distinct compositions. They have these funny Roman numerals and letters attached to them. It doesn't matter what they mean, but the important thing is to see that they're all from different bodies. These are different bodies. These iron meteorites have different compositions, and so we have them all here, which we can go and analyze over here. Now, there are different links between meteorites and asteroids. You could ask, how do we know that meteorites come from asteroids? There are 10 links between them because I have 10 fingers, and so that's as far as I can count. The cooling rates of meteorites indicate that they cooled from high temperatures at rates of about 1 degree per million years to 100 degrees per million years or so. And then we can do some calculations to suggest that they formed from bodies that are a few hundred kilometers across, the same size as the largest asteroids. In order to determine a metallographic cooling rate, we can analyze the composition and the size of metal grains and make diffusion models to see how fast it would take the nickel in the metal grains to diffuse from the center to the edge. And then we can measure that, plot it against these cooling rate curves, and then determine how quickly the asteroids, or how slowly, really, the asteroids cooled. Another link between meteorites and asteroids is the fact that we look at asteroids and we see that they're cratered. They're so-called shock full of craters over here. And if we look at meteorites, we see that they're made of fragments. A lot of them are made of different fragments. We call these kind of meteorites breccias. They've been brecciated, fragmented. It's made of different inclusions and fragments that are broken apart and then cemented back together. That indicates they're from a body that's been peppered with impacts. And so we can see that the asteroids have been. So that's a circumstantial evidence that they're from bodies like asteroids. Jupiter flings asteroids into Earth-crossing orbits, and it's calculated that about 7% of these will eventually strike the Earth. The largest of these things is Sisyphus, and that's 8.5 kilometers across, and that would be bad if that were to hit the Earth. The one that killed the dinosaurs 66 million years ago was about 10 kilometers across, so this is in that same ballpark. That had some significant consequences, and so, oh, there it is. And interestingly, something that no one in here knows, a piece of this meteorite exists. The guy in the office 2 doors from me found it in a deep sea drill core in the Pacific, this 2.5 millimeter piece over here of the asteroid that came 66 million years ago. We don't know with absolute certainty that it is, but it's in a column. It's exactly the same age. It's a highly weathered carbonaceous chondrite meteorite. And there's just nothing else for thousands of miles. Either by a miraculous coincidence, this thing fell in the Pacific Ocean right there in this narrow column at exactly the right age, or it's a chunk of the dinosaur killer over here. And so there it is. That's what happened 66 million years ago. Another one is the cosmic ray exposure ages of these things. What's a cosmic ray exposure age? Well, cosmic rays coming from the galactic cosmic rays are coming from the sun are high energy particles that penetrate a rock to the depth of about a meter or so, and it transmutes some elements into other elements that are radioactive. We can put it in the laboratory, and we can see by looking at the parent and daughter products how long these things have been in space as meter-sized objects. And they've been in space some millions of years, about the same amount of time we can calculate it would take for a body to work its way from the asteroid belt to the Earth. So the cosmic ray exposure ages of the meteorites is another indicator that they come from asteroids. Bodies near the sun have very high concentrations of solar wind implanted noble gases. The solar wind is the expanding corona over here. Going out, it creates our aurorae when it hits our magnetic field there. And when it hits airless bodies like the moon or like asteroids, these particles are implanted in the soil. And so we can measure the abundance of solar wind gases per cubic centimeter, if you will, and we can see, just as the solar wind is expanding and it's getting less dense as it moves through space, we'd expect a certain abundance of these elements at about 3 AU, 3 astronomical units, the distance of the asteroid belt from the sun, and it's the same one that we'd expect. The fact that some meteorites contain solar wind gases at all means they're from relatively small bodies that are airless, and so again, that's another symptom or another characteristic that they are from the asteroid belt. Okay. Now, these meteorites, I'm going to make you guys do a little bit of math here in a moment. You didn't expect you'd get that for the money that you paid, did you? But the old formation ages of these meteorites indicate they come from small bodies. That's because they have high surface to volume ratios. I'll explain that in just a minute. That's where the math comes in just a minute. Small bodies lose their heat very quickly into space. Big bodies have retained their heat. So, let's go look at this. Here's the math part. Let's say that the units here are a centimeter. So here we have a cube that's 1 centimeter on the side. It has 6 surfaces. Each surface is 1 square centimeter. So its total surface area will be 6 square centimeters. Its volume will be 1 times 1 times 1, or 1 cubic centimeter. Its surface to volume ratio will be 6 to 1, or 6. Now, here's a bigger object, 10 centimeters on the side. It has, each side is 10 times 10, or 100 cubic centimeters. So it has 6 sides. It'll have 600 square centimeters. 100 times 100, 100 square centimeters. 600 square centimeters for its surface area. Its volume will be 10 times 10 times 10, or 1,000 cubic centimeters. Its surface to volume ratio is 0.6. So the smaller object has 10 times as much 10 times as great a surface to volume ratio as the bigger object. As we get smaller and smaller and smaller, it essentially becomes all surface. And so that means if it's hot, it'll have radiate its heat quickly because there'll be very little volume compared to its surface, right? So the question is here, this guy is cold, what's he doing? And you'd do the same thing too if your wife took away the covers from you or whatever. And you'd be scrunching down like this, reducing your surface area to minimize your exposure to the cold air. And that's what he's doing over here. So it's the same factor. Surface to volume ratio, it's very important throughout all of science. Okay, so how do we, it's true in biology as well. And so let's look at how the consequences of this. We look at Vesta over here. The rocks are 4.5 billion years old. The last volcanic activity it had on its surface was 4.5 billion years ago. The moon, much bigger, has a lower surface to volume ratio. It had volcanic activity, major volcanic activity, about 1 billion years ago or so. Mars had major volcanic activity about 200 million years ago. The Earth had major volcanic activity, right now. This second, the Earth still has volcanic activity. Volcanoes are erupting as we speak. And so we can see how the surface to volume ratio has affected these things. Another way is we can look at how light is reflected off of meteorites, these so-called spectral reflectivities of these things. We can compare in the laboratory what carbonaceous chondrites look like, what carbonaceous material looks like, what silicates look like, what the mineral ensitite does, and we can compare these to the spectral reflectivities of asteroids and see if their compositions are the same as meteoritic materials. We've identified the orbits of about 30 meteorites as they come in, some from video cameras and some from camera networks. In 2015, Chelyabinsk came in Russia, and the Russians have all these video cams because they have a corrupt system over there. And so in order to prove, after this drunk guy ran into your car, in order to prove it in court that it was his fault, they all have video cameras, so you can show, you have direct evidence that it happened. And so when Chelyabinsk came in, there's lots and lots of videos of Chelyabinsk coming in. You can see them again on YouTube. Okay, and finally, meteorites have been recovered from some asteroids. The Japanese Hayabusa spacecraft retrieved some LL chondrites, some ordinary chondrites from the asteroid Itokawa, and 2 asteroids were actually found just before they crashed into Earth. These are small asteroids. In 2008, this asteroid TC3 was identified as an asteroid about 20 hours before it crashed in the Sudan, and meteorites were recovered from the Sudan. And earlier this year, this asteroid 2018 LA, not named for Los Angeles, however, this was identified 8 hours before it fell in Botswana. Here's the dust trail of the asteroid 2008 TC3. Here's one of the meteorites, a peculiar kind of meteorite called a urolite that was found a couple of months later. It's called Amahata Sitta over here. And with apologies to Mel Brooks, they had to comb the deserts to find these meteorites over here. And here was the discovery of the asteroid earlier this year of 2018 LA over there. And here's one of the meteorite fragments that was found in Botswana right after it crashed in there. It has not yet been characterized. It's still in the lab. So it's not official yet. I want to show you just some neat thing that we can do from asteroids. We can get paleogravity from some of these asteroids. So the gravitational center, you can get up and down from there. But how do we possibly get it? Well, I found this, I was analyzing this meteorite. It's an impact melt from Antarctica, and all these black things are holes. There were bubbles in it, vesicles, if you will. And when I looked at them, I noticed this. On one side are the bubbles, in the middle is sulfide, and the bottom is metal. And you just look at the density. The density of the bubble in the air is nearly 0. The density of the sulfide in between is a density of about 4.5, and the density of metal is about 8. It's almost always oriented in the same way, so that gives us the gravitational direction, paleogravity, if you will, on this parent body. I entitled my paper, "What's Up?" Oh, so how do we look at meteorites? How do we look at asteroids? Well, the first asteroid was discovered on the first night of the 19th century by Piazzi. It's now the largest asteroid. It's now considered a dwarf planet, Ceres. We found another asteroid, well, I didn't, but another asteroid was found in 1802, Pallas, then Juno in 1804, Vesta in 1807. And you can see here, 300 were discovered by 1890. Now there's 790,000 asteroids that have been discovered, and there's about 1 to 2 million that are estimated to be over 1 kilometer in size. Almost all of them are orbiting over there in the asteroid belt over here. If we look at this plot of the inclination above the Earth's orbit, the ecliptic, and distance from the sun, we can see that there's clumps over here called the Themis family, the Eos family, the Coronis family, and so forth. And what are these clumps? These are clumps that were one asteroid that got broken apart by a big impact, and the pieces separated at low relative velocity, and although they're now separate bodies, they retain very similar orbital elements. And so these things, we can trace them back, and they're originally part of one body. These are called Hirayama families over there. About 85% of the asteroids are from these 5 families. The other 15% are probably from families which have sort of dissipated over time and can no longer be seen. There's also these things called Kirkwood gaps after American astronomer Daniel Kirkwood, and we can see that there's a lot of asteroids over here, but at these particular distances there's very few asteroids there. So something must have caused these asteroids to not be in those particular places anymore, and that culprit is Jupiter. At 2.1 AU, an asteroid orbits the Sun in 3 years, which is 1/4 of Jupiter's orbital period of 12 years. And at these different distances, they're simple fractions of Jupiter's orbit. So, for example, at 2.5 astronomical units, 1 astronomical unit being the Earth-Sun distance, an asteroid will orbit the Sun every 4 years, which is 1/3 of Jupiter's orbit. We can see they start off here, the asteroid and Jupiter are in sync, but after 4 years, they're in sync. And it'll kick it out of that orbit. Okay, let's look at some of the sizes of the asteroids that have been visited. Whoop, let's go back here if I can. Itokawa is really tiny, and then some of these other asteroids that we've seen are bigger and bigger and bigger. Finally, we have Vesta here, which is huge compared to the others, but we can see that Vesta is a lot smaller than Ceres, the first asteroid to be discovered and the largest one. Ceres, as we can see, is a lot smaller than the Moon, Mercury, or Mars. So here's sort of like a way that you can sort of look at them over here. Here's a few other pictures of asteroids. There's Waltzing Matilda over there, about 59 kilometers across, Gaspra and Ida. There's Gaspra and Ida actually has a moon. This is one of the, this is actually, the person who discovered this is a friend of ours, and he wanted to name it Elvis, but it didn't sort of go into, conform to the pattern, and so it was named Dactyl because the dactyly had something to do with Ida. I don't remember my mythology well enough. Eros, there we've landed a spacecraft on Eros, and this is a small asteroid that the Japanese spacecraft Hayabusa has gone to. It's Itokawa, and I looked at this and I'm trying to think, what does this look like? What does this remind me of? And it reminded me of a potato, or it reminded me of this, and that makes sense because. That's right. They've taken pictures of Itokawa at the surface, and this is an LL chondrite material, and I have samples at the UCLA Meteorite Gallery that are this big. So we can see some of the samples that are on this asteroid, on the surface of the asteroid, which are similar to the rocks that we have in our meteorite collection there. Some of the samples that were returned are these little fragments. It didn't work completely, the retrieving mechanism, but so they got some dust grains in there, and they showed there was LL composition, and so some of these dust grains were returned. The new spacecraft, Hayabusa 2, is by this other asteroid now. It's bigger, Ryugu. It's bigger than Itokawa, and hopefully that mission will work very well. It sort of looks like a die. It's nearly square in size, and it's taken some of these magnificent pictures over here. We can look at the distribution of asteroids throughout the solar system. We can see that they're different types. That's due to their different spectral reflectivities, the different composition of their surfaces. They conform to different distances from the Sun. Some asteroids of one particular kind are abundant in one place. Asteroids of another kind are abundant in another place. And as we move farther from the Sun, i.e. this way, the asteroids get richer in more organic material and more water. Again, it makes sense because it's cooler farther from the Sun. As I just said. Because these asteroids have retained these distributions of different asteroids at different distances, it suggests that there hasn't been much mixing of the asteroid belt since they formed 4.5 billion years ago. Phobos and Deimos, Fear and Terror, are two of the moon, or the two moons of Mars. Interesting thing about them is that Jonathan Swift predicted them in 1726, even though they weren't discovered until 1877. So the question is, how did Jonathan Swift know about it? After leaving Lilliput, Gulliver went to this land of demented scientists called Laputia, and he was talking about their astronomers when he said they have likewise discovered 2 lesser stars or satellites which revolve around Mars. And the question is, how did he come up with this modest proposal? And because Venus and Mercury have no moons, Earth has 1 moon, Jupiter had 4 moons discovered by Galileo, so he just assumed a geometric progression and assumed Mars had 2 moons. So that was just a lucky guess. Here's some nice pictures of Phobos and Deimos, and some pictures of Ceres, now a dwarf planet as well as an asteroid. and here's the Dawn spacecraft orbiting around it. There's these white spots that they found in these craters on Ceres. These turned out to be salt deposits because Ceres probably had an ocean at some point, and this is probably sodium carbonate. So if you get indigestion, you can go to Ceres, and there you go. So Ceres is a differentiated body, even though it doesn't have a metal core. It has a rocky core, and it has a water ice layer underneath there. It probably had an ocean at one time. A lot of interesting things have happened to Ceres. Okay, so going back to asteroids, they got thermally metamorphosed. So the question would be, what is the heat source? Well, one heat source is the decay of short-lived radioactive elements, such as aluminum-26. That's the one that most people think is the main heat source for metamorphosing these asteroids, heating them up. And it makes sense because we have their decay products, which is magnesium-26. It's there. So we knew that it was an important heat source. It was there. That's the consensus view. However, if aluminum-26 was the primary or sole heat source, we would expect this to happen. We'd expect the asteroids to have this sort of this onion shell. The most metamorphosed meteorites, remember they're the type 6, would be in the core. And as you get closer to the surface, you'd have type 5, type 4, and type 3 at the surface. And so we'd also expect that the type 6s, most deeply buried, would cool the slowest. And as you got closer to the surface, because there's less material above it, the asteroids would cool, the meteorites from these areas would cool progressively faster. So I just said that. So we would expect it to look something like this. So if we had petrologic type, as we say, going from 3 to 4 to 5 to 6, metamorphic grade, and cooling rate, we'd expect the fastest cooling to be over there for the type 3s and the type 6s to have the slowest cooling. That's what we'd predict if this was the correct model, if they were internally heated by the decay of short-lived radioactive elements like aluminum-26. So what do the data show? Let's go to the videotape, as someone once said. And here we go. So remember, it has to go like this. Obviously, the L's don't, the L's don't. And if you look here, this is all a mess here. It doesn't work. So the main prediction of that model is it fails. So what else could have done it? Impacts could do it. Impacts cause heating, as we know. And so let's see if we can do something else. In fact, it does work here because we can look at how these meteorites have been shocked, and we can see if meteorites that are more shocked are also more heated, we'd expect a progression just like this, with the meteorites of higher petrologic type, greater metamorphic grade, being progressively more shocked, and they are. So this suggests that shock heating is perhaps the main source, or one of the main sources, an important source anyway, for heating meteorites. So the bottom line is the greater the degree of shock, the greater the degree of heating, the greater degree of shock. It indicates that shock metamorphism may be the primary source of heating asteroids. And so, in summary, we can deduce the geological history of asteroids by studying their meteoritic debris. We can infer details about the origin of the solar system by analyzing the most primitive chondritic meteorites. We can learn about the evolution of the Moon and Mars by examining meteorites blasted off of these bodies. And we can sample the atmospheres of dying stars by inspecting pre-solar grains in these primitive meteorites. So these realizations have made meteorite collecting more popular in recent years, but as with anything else, caveat emptor. And a case in point is that a couple of weeks ago I went to eBay, and here is a lunar meteorite being sold for $155,000. Look, returns. Seller does not accept returns. It's a chunk of magnetite. I get them about 3 times a week sent to me as possible meteorites, and they're worth, I don't know, 12 cents. But the seller does not accept returns. This is from eBay from not just a couple weeks ago or so. So again, be very careful if you're buying something off eBay. But if you want to see the best local display of meteorites, you need to come to where I work, to the UCLA Meteorite Gallery. And it's in the Geology Building. We're open every day, 9 to 4, Monday through Friday. Sunday, we're open with a docent present. And that's all, folks.
Questions from you for the good doctor. So, any questions out here?
Yes.
Yeah. In terms of the chondrules and the metallic inclusions, how did they form, or what is the origins of them?
Okay. The chondrule origin has been debated for about 200 years, and we're still doing it. I have about a third of my papers on the origin of chondrules, and I have bitter battles with people at scientific conferences about how they form. We all have our own pet ideas, but it seems clear to me that they formed by remelting of pre-existing dust balls, if you will, balls of silicate that have coagulated in the nebula, and they got zapped by some flash melting mechanism such as lightning in the nebula. Now there's a problem with the geophysics or the astrophysics of this, to how to get enough charge separation to cause a lightning bolt. That's still being worked out, but I think looking at the thermal gradient and looking at the petrology of these things, I think it's clear that some sort of flash melting mechanism melted pre-existing fluffy balls of dust to form the chondrules. The refractory inclusions may have formed in a similar way. Some of the original grains probably condensed from the cooling solar nebula gas.
In other words, the little iron.
Well, the iron itself condensed from the gas as it reached a certain temperature. And all the elements condensed from the gas that way, and they formed these little particles which sort of aggregated together by van der Waals forces and things like that into other particles which got zapped, most likely. But we're still fighting about it all the time.
So you I think I heard you in your sort of last statement say contain debris from a dying star?
Yes, I didn't go into that.
So my question with that,
Sure.
right, is so the sun is our star, right, and then everything is exo outside of that, right? So, and these asteroids are in the asteroid belt,
Right.
meter and la la la, but then you have like exoplanets and exostars, I guess, right? So I'm just wondering the relationship between debris from a dying star that is exo and this matter that's in our solar system.
Okay, so there's a giant molecular cloud from which the solar system is forming, and that cloud is enriched in material from other stars that are in that region. When stars die, form supernovae, or they sort of puff off the outer atmosphere, grains condense in their things, and they get injected into the molecular cloud, and these things fall into the solar system. And if you're in an area of the solar system where temperatures are cool enough, these grains can survive and accrete and aggregate together with the materials formed inside the solar system, and we find these 10 micron sized grains from the red giant stars and Wolf-Rayet stars and asymptotic giant branch stars inside some of these primitive meteorites. They've survived, and you can study them and do sort of astrophysics with the ion microprobe to see what the atmospheres of these things are like. So we can do that by looking at these pre-solar grains, as they're called.
So that ultimately means even if in these tiny particles we have matter on this planet that came from outside of our solar system.
Absolutely.
Right?
Isn't that cool? It was first found at University of Chicago by Ed Anders and his group in the early 80s. Hints of it go back to the 60s, though, because we found some isotopic anomalies over there.
Did you mention organic material?
I did. There's kerogens and there's amino acids. The Murchison meteorite, which fell in Australia in '69, is just chock full of amino acids. Now, on Earth, all the amino acids are left-handed because it's more energy efficient for an organism to have all right-handed or left-handed amino acids. On Earth, they're all left-handed. But if you're not produced biologically, you have 50% right and 50% left, as we find in these meteorites. And so they're not produced biologically. We have amino acids there. We have kerogen. We have other soluble and insoluble organic compounds inside of some of these carbonaceous chondrites, up to 1% or 2%. Forming these meteorites. These formed by Fischer-Tropsch reactions and other types of reactions inside the nebula.
Just to get a sense of scale, what is the mass of all the asteroids in the asteroid?
Oh, it's tiny. You actually don't remember. It's I don't know, 0.2% of the Earth or something like that. So yeah, it's small. Now the question is, it's small now. Was it always small? Probably not. There's a lot of evidence that the giant planets have migrated, the so-called the Grand Tack model and the Nice model. And when they were doing these things, a lot of asteroidal material may have gotten kicked out of the solar system. And so what the original abundance of asteroids and planetesimals were is unclear. The different models make different predictions.
My question seems inappropriately terrestrial, but when you were talking about the Devil's Postpile being basalt, did I understand you to say that the Devil's Tower in Wyoming is not?
No, it's not formed the same way. Over at Devil's Postpile, this is a flood basalt which cooled. Over in Wyoming, the Close Encounters thing is a neck, a volcanic neck. It's a different piece of the volcano. It's part of the volcanic structure there, which has survived weathering and alteration and erosion, whereas this is a basalt flow that just oozed out of the volcano on the surface. So it's a different part of the same volcanic structure. I'm sorry if I was unclear.
And how exactly, okay, and based on the previous question, based on his question about the grains coming from dying stars, how do those grains form in those dying stars? Because I've heard that the stars are aptly millions of degrees.
Absolutely. So the question is, but as the atmosphere expands, it cools, and you have this hot gas that gets cooler and cooler and cooler as it gets farther and farther from the star after it explodes, and eventually it gets to a point cool enough that these mineral grains can condense from the gas. They don't do it near the star, they don't do it right away, but they do condense, and then they get put into the interstellar medium, eventually finding their way into H2 regions, molecular clouds, and then stars form from these objects, and so these grains are just sitting around.
Any other questions for Dr. Rubin? One up there.
Did you like the movie Armageddon?
I did not. And I was thinking of actually walking out of it, except one, I'm too cheap because I already paid money for it. And I knew that people would ask me about it. And so I sort of owed it to audience members like yourself to actually have sat through the entire movie so I'd be able to comment on it honestly. My wife liked it. I didn't like it. One of the things that really bugged me was that well, so there's so many things of it. They're on an asteroid, and then they drop something from the asteroid, and what happens to it? It goes like this. Why would that happen? It should take 30 seconds to fall to the ground, but it just falls as if it was in the Earth gravity, which annoyed me. And also, at the end, it breaks in two pieces, and oh, oof. Just execrable. I don't mean to mince words. Yes?
So, is there any plan that if one of these were to come to Earth that we can do anything to stop it?
That's an excellent. This is called planetary safety or mitigation of the asteroid threat. And the best thing to do is what we're doing now is we're putting some money into observing the skies, trying to catalog these things as much as possible. And there's a lot of different surveys doing these things, and they're doing a good job. There's estimates that within the next 10 or 15 years, we'll have like 90% of the bodies cataloged that are bigger than a kilometer or so. And if we know that they're there and we know what their orbits are, we have a better chance of doing something about it. There's different kinds of asteroid mitigation. The one that's ascendant now is called a gravitation or gravity tractor. People are thinking of. You put a huge mass next to the asteroid, and just the mass of it will be enough to nudge the asteroid. If you know about it far enough in advance, and if you just nudge it a little bit, changing its velocity in its orbit by just a few millimeters per second, if you know about it far enough, that may be enough for it to miss the Earth. If you know about it 3 weeks in advance, you're screwed. If you know about it 20 years in advance, you probably can do something about it, depending on how big it is and on the circumstances. But the best thing to do is to try to catalog as many as possible. That's for asteroids. But what about if a comet is coming in, a long period comet that's coming in? There's not much you can do about it, but most of those are they're not as big as large asteroids, but they can be either 10 kilometers across or something like that, the biggest ones. And that would be devastating, and there's just no way to do that. So we're in the middle of a shooting gallery over here, and it is a little bit scary. If you go, again, Google Images, and you look at near-Earth asteroids, and you plot all these things, you can see there's the Earth, and there's just dots everywhere. And it is kind of scary.
How old were you when you started getting interested in meteorites and asteroids, and what was your childhood like?
Well, I have a big brother who's 5 years older than me, and he used to read me science books when I was a little kid before I could read. And I was always interested in space and dinosaurs, like all kids. And when I grew up in Chicago, and I used to go to the Adler Planetarium over there and sit on this half-ton meteorite, Canyon Diablo from Meteor Crater, Arizona, that's sitting there, and it made a big impression on me. I was an astronomy major, but then when I went for my master's degree, I was at the University of Illinois Chicago, which didn't have an astronomy program, so I went into geology, which I liked. I had taken one course in geology, Geology 101 as an undergrad. And the only thing I could think of at the time that mixed geology and astronomy was meteorites. And so then I just started getting into it for my master's and my PhD and my postdoc and so forth. And now out of like 200 or so research papers I have, every single one of them is on meteorites. I have just sort of fallen in love with them because they're so cool. Poor regular astronomers can't hold their beloved objects in their hands. They can only look at them and study them remotely. Sometimes they can't even look through the they don't even look through the telescopes anymore. They just sit at their computer. The technicians do all the work. But I can hold these cosmic objects in my hand and look at them and study them directly. And the tactile sensation of it is really terrific. So I like it a lot better than doing normal astronomy through a telescope.
Over there.
Hi. Hi. With all the missions that are happening now, what are you expecting in your field in the next 5 years to come from some of the missions that have gone out in the last few years?
Well, we're learning more. The sample return is really cool because the meteorites come from unknown bodies. Most people think that the eucrites, howardites, the yajanites, the HETs are from Vesta, but other than that, there's no other asteroid from which we can peg these meteorite kinds from that asteroid. So if we have sample return missions like Hayabusa, Hayabusa 2, and some of these others, OSIRIS-REx, and some of these others that are coming back, we're going to get sort of ground truth. We're going to get pictures and some geophysical data from these bodies as well as samples from them, and that'll teach us a little bit more about their origins. Another really good thing that's happening is that we're getting more and more meteorites. Out of the 68,000 of them, most of them are from hot and cold deserts, from Antarctica and from the Sahara. And so we're having so many more meteorites, we're expanding the number of meteorite groups there are, the number of asteroids that are represented in our collections. And so by expanding the number of bodies that we can investigate, we're learning more and more about the origin of the solar system.
How are they finding those?
Oh, in Antarctica, for example, meteorites fall in Antarctica the same way they fall everywhere else on Earth. It's the same rate. But they get trapped in the ice flows downhill, as ices want to do. Then they hit the transantarctic mountain chain, and then the ice hits it and starts welling up. And it wells up, it sublimates. The ice turns into a gas. But meteorites don't do that. The meteorites just get dumped on the surface. And so you can go to these certain areas called stranding surfaces, and you can see meteorites there. Some of them will have hundreds of meteorites within an acre, if you will. And you can, every southern summer, every austral summer, teams funded by the NSF go down there and they pick up meteorites. And they're brought to Houston, the same place the Apollo samples were, and they're initially characterized there. The samples are published online in the Antarctic Meteorite Bulletin, and then researchers like me wait with bated breath for the nearest bulletin which comes out, and then we order our samples. We just say, I want this one, this one, this one, and this one, and here's why. And then a couple of months later, you get them in the mail. Isn't that cool? And so thank you for funding that. And so I get to study them, and now I don't have to go down and traipse around in Antarctica freezing to death. For those of you who want to lose weight, go to Antarctica. Because the friends of mine have gone there. They can't eat enough to maintain their weight. Even if they're eating high-fat stuff, they're always shivering and freezing to death. And so they, just like if you're training for the Tour de France, they're losing weight. They can't eat enough calories to maintain their weight. So that's a good place to go. Or train for the Tour de France. One of the two. Any other questions? Yes. Well, one more. Okay, go ahead.
Sorry about that. So you mentioned that all the asteroids are coming in from the orbit of Jupiter and Mars.
Right.
What about the outer, like Kuiper Belt?
Excellent. There are a lot of bodies in the Kuiper Belt, but we don't have any of them. There's no mechanism which would knock pieces off and send them to the inner solar system with sufficient frequency that we would expect to have any in our collections yet. It's so unlikely to get a piece from there that we have no representatives from the Kuiper Belt. We have no representatives from the moons of the giant planets, even though they're a lot closer. So none of those are in our collections as far as we know. And so all the bodies that all the meteorites that we have, none are from interstellar space. All the meteorites that we have, we believe, are from the asteroid belt or the moon and Mars, and nowhere else. The calculations would indicate it's just too damned unlikely to get anything from those places. Okay, well, it's getting late, so I think that should be enough. Thank you very much. I'll be here mulling around, so if you want to come talk to me privately, feel free. The rest of you can escape. So, thanks.
Who knew we could get diet advice from a meteorite expert? Anyway, thank you very much, Dr. Rubin. We really, really appreciate you being here tonight.
Thank you. I enjoyed it too. Thank you.